Good morning, everybody, and welcome to the final day of BVE 2010 and the final of the root6 training taster sessions. Today's subject is TCP/IP for broadcast engineers. So this is networking, internet-derived networking for broadcast engineers, for the people who are working in facilities where there are shared storage systems and storage systems that communicate over commodity internet-related networks. As I've said on all our previous training tasters, this is a taster session. It's an intro to an intro, if you will. So what we're going to go through today, it's going to be a bit of a gallop, bit of a sprint, 45 minutes through what would normally take the best part of a day. So forgive me if it's brief and if we do rush, but it hopefully gives you a feel for what you can find out about if you come on one of the root6 training days. So here we go. TCP/IP for broadcast engineers. It's a very dense subject, and you can do whole degrees on this, how internet-derived networks work. But there are, as in most things, some very salient details which, when you've grasped those, you can be 90% of the top expert in the field. I've laid out there just some of the things we'll go over today. A bit of a history of the internet and why what was originally built as a defense-related big network is now ubiquitous and used everywhere, and why your little network at home with your laptop and your desktop and your little wireless router, why that is a real microcosm of how the internet works, and how your network at your place of work, your small office network, why that really is almost a little internet. The OSI 7-layer model, which is often taught as the definitive explanation of how networks work and why it's not really so applicable anymore, why there are better ways of thinking about IP-derived networks. The protocols that travel across the internet, UDP and TCP principally. I mean, there are many others, but those are the important ones that we'll talk about today. Routers, hubs, switches, and how they differ and why it's important to know how they differ and what they're used for. Classes of networks. You might have heard about Class A, Class B, Class C subnets, and maybe you don't know what that's all about, but this will give you a little starter so you can go and fully investigate that. Network address translation, something that's very important, sort of arisen in the last 10 years, and why that's kind of saving the internet from address space overload. And we're going to finish up with just some of the applications in film and television for the storage systems we use for internet protocols, and also for the newer styles of 10 gigabit Ethernet, which are starting to become popular. And then we'll have a little Q&A session at the end. So the internet differs from previous communications networks in that it's a packet switched network. And what does that mean? Well, if you think about when you make a telephone call, you're directly connected via an exchange and via some very clever switching to the person you're talking to. The connection stays alive for the duration of your phone call, and when you hang up, the connection's dropped. And that works. Well, that works when you're designing a phone system in the Victorian age, but it was quite quickly realized in the 1960s that for a resilient and reliable network that would carry many different kinds of information across it, a packet switched network would be required. And I've put some bullet points there that of variable bit data rate streams. So that's really any kind of data you can think about that you can represent as computer information as a bit stream should be able to be carried across this packet switched network. The network has switches and routers and other network node equipment that will manage and administrate that movement of the packets from A to B across the network. And that gives rise to this idea of variable delay. Packets may take an undetermined amount of time to get from where they're going to where they need to be. And so when you've got information that is time sensitive, like audio, that needs to be built into the protocol, how that's dealt with. The advantages, as we've got there, no dedicated circuits. It's ubiquitous. Once you've kind of laid in that fabric, that network, you don't have to consider any special cases. And each circuit can be carrying many different transmissions at once. You're no doubt aware you'll be sitting at your laptop and you've got a web browser open and an email program open and you're listening to the iPlayer, and your connection doesn't care that you're pulling many different kinds of data across it. The disadvantage is that the network has to administer the movement of data across it, and that's an overhead which is now accepted and is well worth the investment. Now this is the very boring and hard part, but is worth mentioning: the idea of layers. If you've done IT at university, you will no doubt have been taught the 7-layer OSI model, which is, and for many years, I did a programming degree in the early 80s, and the OSI model was being taught then, and I believe it still is being taught in universities. And at a very academic level, it's appropriate, but it doesn't really fit how we think about networks today. And that's because as TCP has become the ubiquitous network protocol that we use for everything, applications and methods of transmission and the kind of equipment we use have really settled into more a 4-layer model, something that's better described by what's often referred to as the Cisco Academy model. If you do any Cisco training, that's what you'll be taught, the 4-layer Cisco Academy model. And you can see there the OSI layers are shown in the left-handmost column. Then in the next column, sometimes referred to as the DARPA layers as well, the Cisco Academy layers, they describe what goes on at the application layer, and as you'd expect, that's your web browser, your email program, your FTP program, and that layer talks to the layer below it, which decides, are these TCP or are these UDP communications? What kind of internet communication are we talking about here? That's referred to as the transport layer. Below that, we have the internet layer, and again, we're still in software, we're still inside the operating system of your computer, and that decides what kind of internet protocol are we going to use. Up until now, IPv4, which was the internet protocol established in the early 80s, has been used for everything, but IPv6 is coming along, and if you look in modern operating systems, the current version of Mac or Windows or any of the Linux distributions you might use, IPv6 is an option, and it's starting to become more widely used. And then we're down to the stuff that engineers get interested in, the physical layer, the data layer, what's referred to by Cisco as the network interface layer, and that includes the adapter card, the wired Ethernet card in the back of your PC, or maybe the wireless network adapter, or other diverse technologies, if we're talking about the wider internet, frame relay, ATM, those kind of things. As mentioned, the 7-layer model isn't so useful unless you're getting very academic about this. It describes very generic networks and is equally applicable to very old networking systems like Novell and Token Ring and things that we probably haven't seen since the 80s. So really, if you want to kind of get your head around a network model, the 4-layer Cisco Academy model, ARPANET model, is what you want. And as we've said, you've got the link layer. So we're going back up now. So previously, before I went from the software layer down, but if we go back up again, the link layer, which is all that physical stuff, network cables, the interface card in your computer, or the wireless antenna on the back of your computer, or on your router, or whatever. Then going up another layer, the network layer. What kind of internet protocol traffic are we talking about? Going up again, the transport layer. Is this TCP traffic? Is it UDP traffic? And that will largely be reflected by what's being shoveled across it. If it's web traffic, it's probably coming in over TCP/IP. If it's streamed audio, it's probably coming in over UDP/IP. And then we've got the application layer on top of it, where the programs that use the internet suite, the TCP/IP suite below it, reside. Your web browser, your FTP program, your telnet session. Now, all of this only really works if every computer on this big network of networks has an IP address. And if you've done any under-the-hood work on your PC or your Mac, you'll recognise those two IP addresses up there. And that's called dotted notation, 4-byte dotted notation. So you've got 4 8-bit bytes describing the address of a computer. So if you imagine that top network address there, 192.168.0.22. So how many variations could we have? Well, you've got 256 variations on the first number, 256 on the second, 256 on the third, and all the way to the fourth. So 256 times 256, that's 65,000. Times 256, that's 16 million. Times 256, that's a very large number. And you'd think that would be fine. You would think that every single device on the internet could have its own IP address without any worries. The small fly in this ointment is that the internet has become more ubiquitous than the people who designed it ever imagined. Think about your own home. And whereas a year ago, or 2 or 5 years ago, you might have only had one PC and a little router, nowadays you might have a PC, a laptop, maybe your partner has a laptop, maybe your kids have laptops, Xboxes, Wiis, iPhones. The last time I looked on my router at home, there were 18 live IP addresses in my home. So all of a sudden, the IP address space doesn't look that big anymore. We ran out of IP addresses notionally 10 years ago. The other thing is that not the entire IP address range is usable. Large chunks of the IP address range were reserved for special reasons. And in fact, that first IP address you see there, 192.168.0.22, is part of the reserved IP address space for local area networks. So in your office, it's unlikely that you have an IP address that's particularly unique when you consider the whole internet. I bet when you fire up your machine at home or your machine at your office, you'll find you've got a 192.something IP address. Now that's not a routable IP address because it's reserved for local area networks, and there are large swathes of the IP address space which are thus reserved. The address below it, 83.56.123.78, is a real internet IP address. It happens to be the address of one of the servers at root6, and that's a real network, internet-facing IP address, which other sources on the internet can route to and from. And you're thinking to yourself, well, if I've got an IP address on my laptop which isn't routable across the internet, how on earth am I looking at these web pages? How on earth am I listening to the iPlayer? And we'll get onto that. That's a bit of magic called network address translation that does all that. But just to bear in mind that although every computer on the internet and every device on the internet has to have an IP address, not all of them actually work on the internet, and routers are the clever thing that makes this all hang together. In addition to an IP address, every computer also has to have a subnet mask, which is that 255.255.255.0. That's a typical C-class network subnet mask. And the subnet mask is a way of the equipment, your router or network switch, being able to correctly assign and route internet traffic between machines on a network or on the wider internet. In addition to the subnet mask and the IP address, every device on the internet also has to have an IP address, has to have a MAC address, a media access control address. It's nothing to do with Apple computers. They have to have them as well as PCs and everything else. You'll sometimes hear them referred to as hardware addresses. And that 6 hex number you see below is a typical MAC address. That's the MAC address of my laptop. And they really are unique. Every single device that communicates over Ethernet has to have a separate MAC address. That's very typical. In addition to all this addressing information that a machine has to have to start talking on the internet, traffic travels over ports. Now, way back when, in the 60s, when they were first figuring this all out, the computers that were hung off that seminal ARPANET, that early version of the internet, the ports were actual real individual connectors on the back of the computer. But for many years now, the idea of ports has become virtualized, and the ports now are merely an extension to the protocol. So if a packet arrives at your computer over virtual port 80, by common consent, that's going to be a web packet. That's part of a web page, and there's some other ones there. Port 21 is the file transfer protocol port. Those other ports, 135, 239, and 445, they're the Windows file sharing SMB protocol ports. And then if you've ever used VNC remote control to control the desktop of another computer, that probably happened over port 5900. And in fact, the common consensus is that the low order ports up to 1024 are reserved for well-defined protocols, Windows file sharing, Ethernet, email traffic, web traffic, those kind of things. And the ports above 1024 are kind of purposable. So if you've written a fantastic audio streaming protocol, then you'll typically stick the port above 1024. And there's 65,000 of them. So we've spoken a bit about IP addresses, why machines need those to be able to communicate, ports, what they are, and how traffic flows in and out of computers over these virtualized ports. we can now make reference to the kinds of IP traffic that travel across internet-related networks. And there are many kinds of IP ports, IP packets, but UDP and TCP are the ones that fill the bulk of networks. They're the important ones to know about, and they're the ones that typically, if you're having to set up a hole through a firewall, or maybe set up a VLAN on a Cisco router to route stuff from the graphics department to the editing department, they're the ones you'll need to know about. TCP is the real heavy lifting protocol. It's the one that takes care of lots of stuff for you. When a TCP connection is established, a real virtualized sort of semi-permanent connection between two machines is established. There's a data transfer phase. Once the data's been successfully transferred, the TCP stack will then gracefully close down the connection. And it's this idea of a semi-permanent connection over a packetized network is very much what you should be thinking about with TCP. TCP is very powerful in that it takes care of the ordering and the reception and the retransmission of packets, because across the internet, which is a wild frontier, if you request a website from a server located somewhere else in the world, your request and the data that gets returned to your machine will travel through many, many network nodes, many ISPs, routers and backbones, and because of the nature of the internet, some packets will come one route, some packets will come another route. The network is able to decide what is the best route, on the fly, how to route these packets. And given that a modern web page is probably a megabyte of data, if you go to the front page of Dig or Boing Boing or the BBC, there is a massive amount on that page, pictures, scripts, as well as the HTML that builds the page, maybe a megabyte of data. And that's all been split up into 64 kilobit packets typically. They can be any size really, and delivered across this network. Some of those packets will come different routes, and it's TCP's job to reassemble those packets when they get there, make sure none of them are lost. If any of them are lost, and the network allows for that, TCP has to demand a retransmission of those packets. And to the user, and even to the programmer, you don't have to be aware of that underlying plumbing. You merely open a connection, you open a socket, request something, and as far as you know, it gets there perfectly reliably every single time, because the TCP fragment of the TCP/IP protocol takes care of all that handshaking, retransmission, and making it all work for you. And if you put a network analyzer on a typical bit of the internet, you would see that 90% of the traffic flowing past is TCP/IP traffic. But there's another one which is as important, if not more important, because it provides the kind of utility undergirding of most networks, and that's UDP/IP. User Datagram Protocol is what UDP stands for, and that basically is a lot more lean and mean. It dispenses with all that handshaking nonsense, and it leaves it up to the programmer to make sure that data gets where it needs to go. It merely provides the chance of getting packets from A to B. Doesn't guarantee it, not like TCP. And UDP is more appropriate for things that are more time sensitive. In a moment, we'll go through a typical TCP transaction, but UDP is more appropriate for things where timely delivery of information is important, and you let the software get around the fact that some of the packets will get lost. So streamed media, if you listen to the radio on the iPlayer, you'll no doubt be aware that occasionally you get a sort of stutter effect, or data's lost. Streamed media is typically delivered over UDP, and in a sense it's better that things arrive in a timely manner without all the overhead of handshaking and retransmission and all those things, and it's not such a big deal if you lose a few frames from your YouTube video. That's not so bad. DNS, the domain name system, which is how the very convenient domain names that you type into your browser bar, how they're turned into IP addresses. That works over UDP, because that has to be quick, instant. There's a lot of it going on all the time on the internet, and if you don't get a DNS request back, well, just reissue the request. In fact, if you're familiar with the network settings in Windows, you can define several DNS servers, and if the first DNS server doesn't respond quickly, you make a request to the second one, and hopefully that one returns the IP address related to your domain name very quickly. And then there's the much more lower level kind of plumbing about how local area networks work, DHCP and RIP, those protocols, they all work over UDP. We're going to talk a little bit about DHCP, which is the Dynamic Host Control Protocol, in a moment. So just really to recap, that UDP IP can be thought of as the utility protocol. It's the plumbing that undergirds networks, and TCP IP is the kind of is the heavy lifting protocol. It's the one that most things rely on, and it's the one that kind of takes care of business. We'll quickly just skip over this because this is getting incredibly geeky. There's a little image I stole off Wikipedia, and this shows you what the header of a TCP/IP packet looks like. It's got loads of information in there, the source port, the destination port, because although you might request something on a certain port, you might request a web page on port 80, there's nothing to stop the server returning it on a different port. Sequence numbers, they're important because that allows the equipment along the way to keep track of sequences, and it allows your computer to say, hang on, this packet's arrived out of sequence. I'll have to buffer this one and wait for the previous one to arrive next. Lots of other good stuff going on in the header of a TCP/IP packet, and it's all necessary, and it's all what makes it all work seamlessly. The other thing to remember about TCP is this thing called the TCP handshake. It's what gives TCP part of its power, and it's what adds a lot of overhead to TCP, and it's why typically you don't do things like DNS inquiries over TCP. But the TCP handshake is the first part of establishing this idea of a semi-permanent connection across the internet for traffic to flow. And so typically, if you wanted to set up a TCP connection between two machines, so your laptop, you request a web page, and you want to start up that session of requesting the web page and the web server serving it back with all the assets that belong to the web page, the images, the rich media content. The very first thing that happens is that the client computer will send out what they call a SYN packet. Stands for synchronize. The server at the remote end will respond with a SYN-ACK saying, yes, I got your SYN packet, fantastic. And then finally the client will send an ACK, acknowledgement, back to the server saying, got your SYN-ACK packet, we're ready to go. It's the start of building that TCP connection to allow IP traffic to move between the two computers. One of the interesting upshots of this is that it makes it very. If you're a malicious person, if you're doing bad things on the internet, if you're trying to harvest people's credit card numbers or other things like that, over TCP traffic, it makes it very hard to spoof an IP address, because if you issue a SYN request to a remote server with a fake IP address in the packet header, and then the server responds back to that fake IP address, you'll never get the SYN-ACK packet back. So one of the upshots is that TCP/IP is a more secure protocol than UDP could be considered to be. And lots of organisations, the MOD and places like that, specify that in fact everything has to be done over TCP. So if you're working at an MOD facility, even DNS lookups are done over TCP/IP, which makes their networks a bit more bogged down, but I'm sure they can afford it. So let's extend that to a bit more of a real-world session. When you fire up your laptop or your PC and it gets connected to your router, so this could be at your home or at your place of work, and you fire up a web browser and you request a web page, what really happens? Well, an awful lot of stuff happens. There are many hundreds, if not thousands, of transactions between the two computers involved, and that's even putting aside the various routers and gateways on the packet's way between your house and the web server at Google in the London Internet Exchange, or at Yahoo in Texas, or whatever. But we'll just have a bit of a run through based on the network stuff, the handshaking stuff. So your router's turned on, it's connected to the internet. Your computer's turned on, Windows is booted, or Mac is booted, or Linux is booted, whatever. And you first of all, your machine doesn't have an IP address. Many years ago, we used to hard set the IP addresses of computers, but nowadays it's much more common for your computer to be issued an IP address by a DHCP server on your network, a Dynamic Host Control Protocol server. Now, in a company, that's going to be a proper computer, a big piece of metal sitting in a rack somewhere. On your home network, it's the job of the little £50 router that you bought at Curry's, or maybe came free with your ISP's account. So your computer issues, over UDP, mind you, issues a DHCP discovery request. And because your computer doesn't yet have an IP address, it uses what they call the broadcast address, 255.255.255.255. Now that address only works on local area networks, can't be routed across the internet, but that doesn't matter because you're just trying to get an IP address at this point. So the router, or in the case of a larger network, the DHCP server, responds to the offer with a DHCP offer. And it offers an IP address. There you go, try this one for size. The operating system of the computer that made the original DHCP discovery request now responds with a DHCP request packet. Now we're still working over UDP IP at this point, that's kind of acknowledging that it received the IP address from the DHCP server. Now the next part of the transaction, which kind of closes off the DHCP phase, is the router, or the DHCP server, responds with some other details. It gives you some DNS numbers and lease time, how long that IP address is going to be good for. If you've paid any attention at home, you might have noticed that your internet router at home, which is given a DHCP IP address by your service provider, your internet address changes periodically. It's not always the same. In fact, if you want a fixed one, so that you can be sure of being able to connect to your router from outside, on the big bad internet, you have to pay a little bit more to your ISP for a fixed IP address in most cases. So that's the sort of the DHCP phase of a connection. So all we've achieved up to this point with this little to and fro between the PC and the router is the PC now has been furnished with an IP address, so it knows how to behave nicely on the network, and it's also got some other information. It's got the IP address of a DNS server, so it knows how to turn domain names, www.root6.com, into the IP address of the web server that will respond to those requests, and we're ready to go. So now your PC has got all that, and you type into your web browser www.root6.com or whatever. Firefox, or whatever web browser you're using, Internet Explorer or Safari, which is running at the application layer, if you remember our 4-layer model, that makes a request, the transport layer, which is part of the operating system. It's part of what we refer to as the TCP/IP stack for that domain name. It says, I want to go to www.root6.com. The transport layer checks to see if you've ever been there before, and has it made a little cached record of the IP address of that server, and if it hasn't, it passes that DNS request down to the network layer. The network layer says, okay, are we going out on over the Ethernet cable or the wireless connection, or maybe you've got one of those USB ADSL modems, and it sends the request out over the appropriate network interface. And remember, we're still UDP because this is a DNS request, and that would use UDP port 53. The router then proxies that DNS request, sends it out to the big bad internet, and at some point a DNS server will intercept that. It might be the ISP's DNS server, or it might be a higher level DNS server, depending on whether anybody else who's on your ISP has ever been to that domain before. And eventually your router will be returned the appropriate IP address of that web server. In the case of Root6's web server, it's that number down there, 193.203.84.196. The router will then return the result of that DNS lookup, again over UDP port 53 to your PC. So now your PC knows where on the internet with an IP address where it can find that web server. So now the application, which Firefox, Safari, whatever your web browser is, has that IP address to hand. It can start making requests for web pages. So the transport layer of your operating system's IP stack initiates a TCP session, which the network layer takes care of in terms of which IP port it's being sent out to the back of the machine on port 80 for web traffic. And it will send a request to your local router, because remember this is a little local area network, for whatever web page might get served up by that IP address that we've already found out. So you can see that eventually you'll start getting packets back from the remote web server back to your PC, and your PC can start building the web page that you requested. If it's an even halfway complicated web page, this happens hundreds, if not thousands, of times to build that web page, which will be composed of some HTML, some scripts, some images, maybe some rich media. And so you can see that at that very nitty-gritty network packet level, there's an awful lot going on, and it's going on very quickly. People often say that computers are no more complicated than a bag of rocks, but they're a bag of rocks that can do things very, very quickly, very simple things very, very quickly. And you barely notice that. You know, you ask for that web page, and within a second it's there on your screen, and you've largely been unaware of the hundreds, if not thousands, of transactions that have happened between your machine and your router, and the router and the web server that was somewhere out there on the internet, maybe 10 miles away, maybe 12,000 miles away, who knows. And the fact of the matter is the network just takes care of it. Now there's a myriad of protocols that I haven't even referred to that allow all this to happen, but they really are beyond the scope of our little 45-minute dash through our day-long course. The heavy lifting protocols like BGP, the Border Gateway Protocol, which allow packets to successfully traverse the internet, all the unavoidable TCP/IP retries as packets were lost, Address Resolution Protocol, which happens in your router, that allows your router to take care of IP and MAC address translation, and any negotiations that your wireless PC may have had to make to set this all up. These were all going on as well, and really they're beyond the scope of today's talk. We made reference earlier to network classes. Now, when the internet was originally envisaged with those 4 dotted notation IP addresses, the idea was that those IP addresses wouldn't just be randomly assigned, that it's a classful network, that you'd be able to get some useful information from those IP addresses for aiding the routing of your packets across the network. I mean, nowadays you could imagine that a router could quite easily maintain a database of where every single IP address was on the internet, because there's only a few hundred million of them, and that's not beyond the scope of a modern database. But back in the 70s and the 60s, when this was all being figured out, that really was beyond the scope of computers of the day. And so the idea was that you would encode into the network address, the IP address, some routing information. You would know that certain areas of the internet would be under these network addresses, certain areas of the internet would be under those network addresses. And so the idea of network classes basically dictate how this network of networks hangs together in a topological sense, in a geographic sense. In the early years, the internet assigned naming authority handed out whole blocks of network addresses far too readily, and that's what led to the almost run out of internet addresses 10 years ago. The great shortage of IP addresses of the mid-90s. And it was really only a development in technology that saved us, and that was network address translation. So as we sort of hinted at before, the typical network address that most computers you'll ever use will have is not an internet routable network address. It's something like 192.168.something.something. And that's not an address that's routable across the internet, if for no other reason than somebody in the company down the road will be using that address as well. And so this gives rise to this idea of a network of networks. Network address translation basically says you can have a little tiny internet in your office, in your home, and so long as the device that's at the gateway between the big bad internet and your little internet knows the range of addresses on either side of it, it will happily route stuff across itself, taking record of who requested web traffic, who requested iPlayer traffic, who requested Skype traffic, so that when stuff comes back from the requesting server, it can successfully route it back to the machine in question. So in a very real sense, network address translation, NAT, as people always refer to it, is the thing that kind of saved IPv4. IPv4 is the current and contemporary protocol that's used for the vast majority of the time across the internet. IPv6 will catch on eventually, and that kind of spotted this problem before NAT solved it. And so IPv6, I think the famous quote is that IPv6 allows 4 IP addresses for every molecule on the planet. So hopefully that will mean we won't run out of IP addresses as quickly as we did with IPv4. NAT is very useful in that it obscures your little network at the office or at home from the rest of the internet. And as we know, that's a good thing nowadays. There's a lot of bad people out there. And network address translation is an inherently firewall type technology, because a net router will only pass stuff back across it if it knows it was requested from the internal network. It basically turns away all the traffic that wasn't requested. So if a machine inside the network wasn't requesting pages from your bank or whatever, but somebody's trying to inject those back into your network, they're turned away by the net router. So we've made reference to routers, but there's also some other network devices that you'll no doubt have to deal with if you're engineering in a small or a large facility. Routers and switches and hubs, they're the 3 things people talk about. Hubs are not very common anymore, but it's worth mentioning them because they illustrate an aspect of what we're talking about. So if you imagine every single machine on your network's got a little RJ45 connector on the back, and you plug an Ethernet cable into it, and that cable runs back to a router or a network switch to get you onto the network. You might think to yourself, well, so what on earth's the difference between a router and a switch? And I've heard about hubs. How do they differ? A hub is, or they used to be referred to as switches, or a switching hub, is a small gadget that basically just electrically amalgamates a lot of connections. So if there's traffic on one piece of network cable, it gets mirrored onto every other port of the hub. And for a modest little network, that's fine. But when your network gets reasonably busy, when you've got iPlayer going up one channel and you're transferring a big file up to another machine, you don't want to have all those network packets replicated on every single port of the hub, because it's just not appropriate. And so, 10 or 15 years ago, switches became a lot more popular, and that's physically looks the same as a hub. Many Ethernet ports, many machines can be connected, but it maintains a small table inside itself which keeps a record of what machines are where on the network. So it takes a little record of that MAC address, that hardware address of the network card that we talked about, and it knows that if you're copying a large file between machine A, which is on that port of the hub, that port of the network switch, and machine B on that port of the network switch, that's the only places that traffic has to go. It doesn't have to replicate it on all the other ports. Nobody else is interested that those 2 machines are copying a big file between them. And so all of a sudden, network segregation, network fragmentation becomes your friend. It makes sure your network isn't overly congested. A router is kind of the final part of that little puzzle, because the router is the gadget that sits between dissimilar networks. So you've got your office local area network, and a lot of stuff goes on there. The graphics department copies stuff to the editing department, and the editing department sends stuff to other people, and it all kind of works. But of course, a lot of the time, network traffic is intended to go out of your network. And so a router is the device that sits between 2 networks, and it knows all about the IP address range on one side of itself, typically that 192.168, unroutable network addresses that won't work on the internet. And it knows about the other side of the router, the big bad internet, or where everything is to be found. And it sends stuff across itself as appropriate. If it sees packets that it knows are intended to move between machines on the local area network, it doesn't bother sending those out across the internet. And likewise, when it sees packets on the internet that it knows aren't intended for things on the other side of itself, it won't route them across. So network address translation and routers are very much synonymous nowadays. Now, as we've said a few times, that your office network or your little home network can be considered a microcosm of the internet. You'd probably appreciate that the little £100 Wi-Fi thing that BT gave you, or that you bought in Curry's, although it does the same job as a data center router, it's a different kind of class of beast. When you see data center switches with thousands of ports on them and sort of £500,000 price tags, you realise that although they're related, they're not the same gadget that you've got sitting under the stairs at home. Applications to storage in film and television. Really, as shared storage systems became popular, starting really in the late 90s. For a long time, anything that required serious amounts of bandwidth to transfer digital video was done over fibre channel networks, where you had expensive, glass optical cabling and expensive fibre channel devices, and things were directly connected to storage area networks, that might have been an Avid Unity or something of that order. Very expensive system, not at all what you consider commodity hardware, not the kind of thing you'd have at home. But in recent years, people have seen the value of providing real Ethernet TCP/IP type connectivity to those storage systems. And so, really for the last 10 years, if you've bought yourself an Apple XSAN or a Facilis Terablock or any other fibre channel type shared storage system where you've got several Avids or several Final Cuts hanging off it, they've also had the option of hanging a dedicated machine that will reshare that storage out over the Ethernet. So, because the guys in graphics who just need to grab a still frame from a program, they don't need fast, multiple channels of digital video access. They just need to grab a frame every couple of times a day, or whatever. And so, there's always been the option of being able to grab off your facility shared storage system over Ethernet. But it's always been considered the kind of poor cousin, the it just works but don't expect much from it type option. However, in the last couple of years, Ethernet has become a much more serious contender as a networking protocol for shared systems in television and film. And there are several sort of mainstream tier 1 type shared storage products now, like Avid, Unity ISIS, SATA Beast, Isilon's 1FS network, all of which root6 sell if you have an interest. They all now rely largely on gigabit Ethernet. So using the kinds of protocols that you use to send your email or to copy a file off the file server in the office, or to use that shared printer down in accounts or whatever. Television and film storage systems are heading much more in that direction. And although contemporary Ethernet, as you have at home, is probably only 100 megabit Ethernet, referred to as 100 base T, and the Ethernet you have in the office is probably gigabit Ethernet, 1000 base T, 1000 megabits of data a second. 10 gigabit Ethernet is taking hold, and more wiser use of Ethernet connections, large frames, and other techniques have allowed Ethernet to really step up as a shared storage system for film and television. And that's why, if you're a jobbing engineer in a facility or a TV studio, or working on OBs, Ethernet can't be ignored. It's not the kind of thing that you can just say, the IT guy deals with it, I don't really care, because in the same way that VTRs have been our bread and butter for 50 years, for the next 50 years, IP will be our bread and butter. It's not the kind of thing that broadcast engineers can afford to take no interest in. Now, I alluded to 10 gigabit Ethernet, which is a technology that's been around for a couple of years and is really starting to take hold. The thing that will really put it into the mainstream is the fact that the next generation of Mac Pro workstations come with 10 gigabit Ethernet on the computer. And once they're doing it, Dell will do it, and everybody will do it. And it won't be a £1,500 add-on card anymore. It'll come with the computer. And at that point, it'll become what gigabit Ethernet was 10 years ago. And I guarantee in 5 years, you'll probably have 10 gigabit Ethernet under the stairs at home for your home network. We've done a bit of work installing those networks. They're a bit different to traditional gigabit Ethernet networks. There's some details there about the cabling and how the data rates have increased and how that all works. But that's probably something for another time, and is probably a bit more low level than you expected today. But just bear that in mind. 10 gigabit is just over the horizon.